This problem looks relatively simple. We'll see it's a block of mass m sitting on an inclined surface. So sitting on a surface that isn't horizontal, and it's inclined at an angle theta. So this is the kind of situation that, in the absence of friction and things, this block can just slide on down the incline. So one thing we might want to know about this problem here is, well, what's its acceleration? If we know the acceleration, then we can start predicting things about maybe how fast it'll be going at the end of the incline and so on. So let's just work on that then. Turns out Newton's law can deliver a nice answer to us on that. We have the two equations, x and y. We'll identify forces, draw signs on there, fill in the equations 1 and 2, and see what we get. So the weird thing about these problems here that often confuses people and maybe isn't the best way to do them, but it's the way sort of your book tells you to do it, is what are you going to put for an x and y coordinate system? Turns out if you take an x, y coordinate system and orient it like this, say you put the y coordinate like this and the x coordinate like this, the way you'd be used to, this isn't the most convenient because there's no axis that's sort of parallel to the motion you might expect. We're expecting this block to sort of slide and stay on this incline right here, and if we put a coordinate system on this, it isn't either along the y or x axis, so it makes the analysis sort of complicated. So what we'll do then is we're just going to take that coordinate system, which maybe we're used to, and we're just going to rotate it like this. So we'll call this the x-axis and this the y-axis, and then see what we get. Because it doesn't matter how we orient the axis, it doesn't have to look pretty to us, as long as we have two orthogonal axes, that'll do. So here's a good y-axis, and here's a good x-axis. So we'll just label that x, and we'll label that y. And there's the coordinate system right there. So what we'll do then is that's, at least the coordinate system, and so this equation would apply along this axis. This one here will apply along this axis. In either case, steps 3 and 4 are the same. Let's see if we can identify those forces. Okay, so we'll get on M here. What I see right off is, of course, M has its weight pulling down on it. We'll just label that mg. And it is sitting on a surface, so it'll have a normal force on it like that. We'll just label that m like that. So those are really the only two forces acting on that mass. Okay, and so what we'll get going with then now is, since those are the only two forces acting on the mass, let's go back to Newton's law and see, let's identify the signs. So we're getting ahead of myself. Let's go identify the signs. I guess we can call this a negative mg because it's down there, and we'll call normal force up like that. That'll be fine like that. That's about it for the sign convention, two signs, two forces. Now what I'll do is I'll just go and fill in the equations 1 and 2 for this and see what we get. Okay? If I'm going to deal with the x-axis now, I'll have to identify some x forces. Now, it doesn't look like on the onset there are any x forces because n is all on the y-axis and mg is sort of between the two. But, of course, when a force is between two axes, it'll have a component along the x and a component along the y, and it's very important to get that right. So here's the x component of gravity, and here's the y component of gravity. And if this is angle theta, that'll be theta right there, and I'll call this mg times the sine of theta. Now, if you watch another video, we call this F sub s here, or sort of the sliding force. Very convenient to sort of have that in your head that when something sits on an incline, there's an mg sine theta, which would want to cause it to slide down the incline, and there it is. There's where it comes from. And the force over here, this other component, is going to be an mg times the cosine theta. So now you have more forces that, because you've identified these components, you can pop back to step 4 and identify some more signs. In particular, if the normal force is up here and positive, the other force, this component over here, will be downwards and negative right there, because normal force is up, and this one here is downwards or negative. And likewise, if you want to call this mg sine theta the sliding force, which you now have, and you can call that negative if you want, because that's sort of along the negative x-axis like that, not the positive x-axis. That'll be just fine. All right, so let's just hit Newton's laws now and see what we get. It's only one mass here, so we only have one application of both equations. So the x acceleration I'd fill in this is the sum of the x forces. So what do I have along the x-axis? Only one force, just the sliding force. I have a minus mg times the sine of theta down. And if I divide that by m, that's Newton's laws. And I can even cancel the m's and say the x acceleration is just minus g times the sine of theta. And indeed, that's the answer right there. That's the acceleration that would cause the block to slide down the incline, minus g sine theta. There's another application of Newton's law along the other axis here, in particular the y forces. Now, if I sum the y forces, let's see what I get. In the y direction here, I have a normal force up and an mg cosine theta down. So I'll go ahead and fill that in. I have a plus n minus mg times the cosine theta down, all that over m. That's another equation. Now, what do I do with this thing? Well, we said it a few times before in other videos. There's nothing in the problem that says this m is going to rise off the incline or fall into it, at least the surface anyway. It stays on the surface. So if the problem starts with a Vy is equal to 0, no y velocity, and if Ay remains 0, this condition here will guarantee that block will stay on the surface. So okay, AY is equal to 0. Just drop down here and say, all right, AY is equal to 0. We get n minus mg times the cosine theta, all that over m. That condition tells us essentially the normal force, n is equal to mg times the cosine of theta. And you can put a big box around that. We don't need to do anything with it in this equation right here because there's nothing to put it into, but it at least tells us the normal force. And it's nice to highlight here that this normal force is not equal to mg. The way a lot of people like to memorize on an inclined surface is mg cosine theta. So the problem is essentially solved. The acceleration that would cause the block to slide down the incline is right here, g times the sine of theta. There it is, and that's essentially the answer. Now there's one other way of getting at this here, which is really the same, but if you sort of feel comfortable like you're mastering all this sort of stuff here, whenever you hit a problem like this, you can sort of dispense with much of the work you've done, depending on how confident you are with your application of Newton laws and sort of what your professor is going to allow and so on. But it's as simple as this. Whenever you have an object on an incline, and I don't care what else it might be doing, there could be friction and ropes and tension and all other kind of stuff in the problem, but the very fact that it's on an incline, it's inclined to some angle theta, I don't care what else is happening to it, you just walk right up to it and say there's going to be a sliding force on F sub s, just put it on there, and F sub s is always going to be mg times the sine of theta. This is the force that causes the object to want to slide down the incline if it has a mass m, and off you'll go. And now you can continue with the rest of the problem. If you don't understand where this came from, look at the problem that we just solved and notice that the sliding force is a component of gravity, the opposite component. So it's an mg sine theta, but if you want to cut down on your work and you're getting more confident with these problems, you just go, look, hey, here's a block on an incline, the incline is some angle theta, the sliding force that wants to pull it down the incline is mg sine theta, end of story, and just continue with the problem.